All right, so welcome to workshop number 2, everybody. We're going to cover number theory this week. So we'll go into a few different subtopics in number theory and explain a few of the basic concepts and then cover some examples. And we'll have a Kahoot part of the way through, just to make sure you understood what we were saying. So number theory in like Math 1141 or high school calculus or something, usually dealing with equations in real numbers. So there's more possible solutions to equations like that. Whereas if you restrict yourself to stuff like integers or natural numbers, there are fewer solutions, and sometimes that makes things easier because you can case bash, and sometimes it makes things more tricky. So number theory is notorious for having questions that are easy to state, but hard to prove and hard to understand the proofs for, because of this weird discrete aspect. So this is a pretty famous one. Fermat's last theorem was actually conjectured by a lawyer, not a mathematician, but the proof is about 93 pages long, and it relies on some things you wouldn't learn in an undergraduate maths course. Quite a few things, actually. So the main things we're going to cover today are divisibility, primality, and also Euler arithmetic. But there's also other things you can look at, like partitioning, which is looking at what numbers add up to a particular number. And also you'll find that there's a lot of algebra in number theory, but it's slightly different to how you would use algebra in a continuous context, because it's not a continuous context. So I'm going to get you all to join a Kahoot, but we're only going to run about 5 questions at a time as we cover the different topics. And I'll share that code now. Okay, so I'll put that code in chat in case somebody hasn't joined, but we probably won't use this until we get to the end of pieces of content. Cool. Great. So we'll start off with modular arithmetic. The key thing to understand in modular arithmetic is it's based around a different concept of what it means for two quantities to be equivalent. Let me just let somebody in. we have three different equivalent ways to define what it means for two numbers to be equivalent modulo n. And all these numbers that we're going to deal with in this workshop will be whole numbers, with the exception of a few rational numbers. So we say that two numbers are equivalent modulo n if their difference is a multiple of n. You can also say that they're, which is just a rearrangement of that first equation. And you can also say that they have the same remainder when divided by n, which might be something you've touched since primary school, but so an example would be 4 is equivalent to 13 and equivalent to 5 mod 9. So what that means is they differ by a multiple of 9, all three of those. And you can write each one as a multiple of 9 plus one of the others. And if you divide them by 9, they all have the same remainder. So another example would be, if you look at the numbers 0, 1, 2, 3, mod 3, they're equivalent respectively to 3, 4, 5, 6. And you can see that kind of when you count up in modular arithmetic, you start at 0, and then you go to 1, and then 2, and then 3. But 3 is the same as 0. So if you were to count up in modular arithmetic, the simplest name for each number would be 0, 1, 2, 0, 1, 2, 0, 1, 2, rather than just keeping counting up forever. So the reason we write it as 3 horizontal lines is because it's very similar to equality, but it's kind of a simpler version of equality, or it's a more generous version of equality that lets more numbers be equal. So if you have 3 equivalent to 7 and 7 equivalent to 15, then you know that 3 is equivalent to 15 in whatever modulus, as long as the modulus is the same. And that's just the same as what you'd see with regular equality. Another thing is it's reflexive, which means every number is modulo equivalent to itself in any modulus. And the final important property is that it's symmetric. So if you look at definition number 3, that's probably the most intuitive way to understand these 3 properties, because it's talking about them being the same in some sense. Of course, A and A have the same remainder when divided by n. And of course, if A and B have the same remainder, then B and A have the same remainder. So I think definition number 3 is probably the most important one to keep in your mind, as long as you remember what it means to divide integers that way. So I think we'll just run through a few of these. You don't need to remember all of them, but the first few about addition, multiplication, exponentiation are pretty important. Like we saw before, 3 is equivalent to 0 mod 3. In general, when you divide a number by itself, it has a remainder of 0. We also have multiplication and addition behaving nicely under modular equivalence. So by nicely, we mean that you can do the same thing to both sides of the equation, equation in big air quotation marks. And as long as you keep the same modulus, you'll have the same, it will still be true if you do the same thing to both sides. There's also a few other properties regarding primes that you don't have to know, but they're nice to know. I'll let you stare at them. I won't go into them too much because they're not so relevant for this workshop. Cool. Does anybody have any questions at the moment? Great. Ethan, were you taking this question?
Yeah. I'm not sure if we want to give them some time to go through it as all.
Actually, we should go through the Kahoot first of all.
Fair point.
Great. Hello. I'll give you some time to join the Kahoot if you haven't already. All right, great. We're starting now. Perfect. Oh, that's not good. Buggy. Yeah, so the polynomial equivalence property comes from the fact that multiplication and addition behave nicely under modular equivalence. If you do the same thing to both sides by adding and multiplying or taking powers, then you'll end up with the same result, or the equation will have the same truth value. It will still be true. Does somebody want to explain where they got confused on that? Cool. Time pressure, yes. I think these questions are all 20 seconds, so it's a bit tough, but just do the best you can. And hopefully you'll remember something from here. The lawyer is winning. Okay, wonderful. Great. So people said it was 1. If you take -1 to the 7 mod 7, because the exponentiation behaves nicely, -1 to the 7 mod 7 will still be -1. I don't blame you for not getting this, but that's one example of how you could have worked out that it couldn't be 1 or -1 And it certainly can't be 0 because 1 to the 7 mod 7 is just 1. Does anybody have particular confusions about that one? Cool. I will say that in general, if P is a prime, then A to the P is going to be equivalent to A mod P. That's called Fermat's little theorem, which is not to be confused with Fermat's last theorem. Great. Z is winning. Perfect. Cool. Okay. If you take that second equivalence there, BC is equivalent to D mod N, and you multiply by A. Oh, that's not good. If you multiply both sides by A, you'll get ABC is equivalent to AD. And we also know that AB is equivalent to 1. So we can actually substitute that in like we would do with a regular equation. So if you multiply both sides by A, you have ABC is equivalent to AD. So that's the same as C is equivalent to AD. And when you're writing this down, you should always write mod N at the end of every equivalence, just to be clear which kind of modular equivalence you're talking about. We'll get into some examples now.
Okie dokie. Should I just start explaining this, or do we want to give them a little bit of time to kind of go over what's happening here? So I can kind of explain the question, what it's asking first, maybe?
Yeah, good idea.
So we're asked to, so this is kind of a ambiguous question. You could be proving it or disproving it. So it's good to do some experimentation beforehand. But basically, we're asked to find a set of 2,000 distinct positive integers such that the sum of the members of every subset is not a perfect square. So what this means is I have to find the annotate menu. There it is. Okay, so we have, let's go with like 5 numbers, right? 1, 2, 3, 4, 5, whatever. And we need to see if the sum of the members of every subset is not a perfect square. So say we had 1 and 2. If we add them together, we get 3, which is not a perfect square. So that one's fine. If we instead had 4 on its own is another subset. So just 4 on its own is 2 squared. So we call this here a perfect square because it's some integer, n to the power of 2, right? So we're trying to find some set of numbers. This is 5. We're trying to find 2,000 positive integers such that no matter what you add together from them, it'll always be, say, 3 or like 5, something that isn't a perfect square. So I might, should we give time to kind of go through it yourself? I think one thing I will mention before we begin is a theorem that comes in, well, not necessarily a theorem, but a property of perfect squares, which is very useful for modular arithmetic. And it has to do with the number 4, which is, say you took any number n and you square it, then this is equivalent to either 0 or 1 mod 4. And to see this, we can take, say, n is an odd number, right? So it's 2k plus 1, and we square it, and we get 4k squared plus 4k plus 1. So if we find the remainder when divided by 4, this divides through by 4, this divides through by 4, this is the only bit that's left over, so we get mod 1. If we were to do a even number and square that, then we get 4k squared, which is very clearly divisible by 4, so we get 0. So if we were looking for, say, distinct positive integers such that the sum of the members is not a perfect square, so we were trying to show that it's true, maybe we should try looking if we can get all of the sums to be equivalent to maybe 3 mod 4. Now, obviously, this doesn't really work, because if you have 3 and say you went 4 above that and you got 7, if you add them together, you're going to get 10, which is 2. And if you keep adding things along, you're going to so when I'm talking about 2 here, I mean mod 4, right? So you're going to get 2, it's equivalent to 2 mod 4. And if you continue working with that, you're going to get 1 mod 4, which could be a perfect square, not always, but it could be a perfect square. So you can't just look for numbers that are equivalent to 3 or equivalent to 2 mod 4, because it won't always get you what you want. You have to think a little bit kind of harder than that, unfortunately. So do we want to give, this is kind of the crux of the argument. Do we want to give them a little bit of time to go through?
I think let's give people 2 minutes to go through this.
Okay, cool. So I'll leave that up just in case. Clean it up. I think it's been about 2 minutes. So I guess I'll continue from here.
Does anybody want to share anything that they came up with? Doesn't have to be a full solution.
No, any ideas? Or any, if you have maybe a possible set of things that might work here, or if you have managed to find a proof that it doesn't work. So a proof by contradiction, maybe. So we could approach this from, so if we're proving that there is a set of distinct integers, maybe we could show that. So if there's a set of distinct integers, that's like saying, well, assume there's no such set, right? And maybe we could approach that. It's a little bit difficult because then we have to try and construct a set or come up with an arbitrary set that kind of disproves it. In this case, proof by contradiction might end up being a little bit circular. You start off with like, we assume that there is no set that satisfies these conditions, and then we show that there is a set, which is basically just saying there is a set to begin with.
I will say that if you're trying to prove that there isn't a set, proof by contradiction is a perfect way to go about it here.
Yes, yes. So you assume there is a set, And then you end up going, hang on a minute, if there's a set, then we contradict some kind of assumption, right? Which is maybe what you're going for there. I was thinking about it the wrong way. Okay, so instead of, okay, first things first, there is a solution to this. The solution that I came up with is 3 times 4 to the k, where k ranges from 1 to 2000. So that's 2000 distinct integers. They're all positive. And from them, hang on, next slide. Yep. So we have a set of integers, and we have 3 times 4 to the I. So coming up with this is kind of the difficult part. Once you come up with it, you can it's just modular arithmetic from this point. But if we think about how we could come up with these numbers, first of all, I know 3 is not a perfect square, right? It is 3 mod 4, so it can't be a perfect square, even if it was not obvious that it's not a square of a number. And if we think, okay, if 3 is included in any sum, we want to use maybe the addition property. So if we have 4 times k for any number, that also can't be a perfect square. If we add 4 times k prime, so another number, that also can't be a perfect square, right? Hang on a minute. Sorry. We could try and reduce Z to Z mod 4, and then look at sums of 0, 1, 2, and 3, and then try to construct a set that doesn't work from there. Yeah, you could. What I'm going at here, though, is if we start off with some number that definitely isn't, and we add any multiple of 4, then we're kind of like, we're not going to get out of the set. The problem, of course, being because it's any subset that we're dealing with, we could just have those powers of 4, and that might cause issues, right? However, or multiples of 4 rather. However, if we take out any 4 here, we get like k plus k prime plus whatever else is there. If we can ensure that this is also 3 mod 4, then we're fine as well there, right? Because this can't be a perfect square, and we're multiplying by 4, which is like 2 times 2, right? So if this has an odd prime factor, for example, a 3, if this has an odd prime factor in it, we cannot end up with, we can't end up with a perfect square. So that's the approach that we came at from here. So if we factor out a 4, we're always going to end up with, so I'll just clear it real quick. If we have 3 plus 4, 3 times 4 to the k, and then maybe like 3 times 4 to the, I don't know, k plus 1, right? The next one along. This, if we, so on its own, it's fine because it's 3 mod 4. But if we were to remove the 3 and just consider those 4s, if we factor out 4 to the k, then we end up just removing this and removing this, right? And this is now not a perfect square. So another property of perfect squares is if you have a perfect square and you multiply it by something that's not a perfect square, you can't get something that is a perfect square, right? Because everything that is a perfect square here, everything that's a perfect square from this has a matching prime factor within the within the number. So there's going to be an odd factor here. It'll be 3 times, I don't know, u squared, right? This is a perfect square, but this odd factor here can't be matched with anything in the 4 to the k, right? So we choose these numbers, I'll just clear the whole thing. So we choose these numbers based on making sure that when we add them together, we can always kind of get a perfect square multiplied by something we know is definitely not a perfect square. We always have some kind of odd factor at work here, right? So we can always factor out the 4 to the k. And if we assume it was a perfect square, so this is a little bit more formal what I was just saying. If we assume that this was a perfect square, then we could write it as n squared for some integer n, right? However, if we were to do that, then we could take u is n and then just divide through by 2 to the minus k, so that when we square it, we end up just getting 4 to the k, 3 plus 4 to the k prime x divide that by 4 to the k, you end up just getting the 3 plus part, right? And this must be a perfect square because n has enough factors so that when you square the whole thing and cancel out all of them, you still get an integer. The 3 plus 4 to the k prime x is an integer, right? So it must be a perfect square, but that's 3 mod 4, right? So this is where we use a contradiction as kind of part of our proof here, right? We're assuming, hey, it might be a perfect square, but then it would have 3 mod 4 as its remainder, which is impossible. Like earlier, we said 0, 1, can't be 3. So any perfect square, we have n squared is 0 squared, 1 squared, 2 squared, or 3 squared, right? And all of them are 0 or 1 mod 4 if you just do the maths. So like 9 mod 4, you're getting 8 plus 1, so it has remained 1. 1 squared is just 1, obviously. 0 squared is just 0. 2 squared is 4, which is 0 mod 4 because it is a factor of 4. So we've got our contradiction. Since all perfect squares have remainder 0 or 1, we have a contradiction. And from that, we know that none of the sums, so it's a sub-contradiction proof, none of the sums here can be a perfect square. So since every sum can't be a perfect square, we have found a set of 2,000 distinct positive integers such that the sum of these members of every subset is not a perfect square. And in fact, this works for any number. They could put 2, they could put 2 million, they could put infinitely many, right? It all relies on being able to factor out the 4 to the k here, which we come about just from 2 main properties. First of all, remainder being 0 or 1 for a perfect square. And second of all, trying to find a way to have an odd factor if we factor anything out of it. Okay, anyone have any questions about that? Finding this construction is something that is kind of more experimental. You have to fiddle around with properties. There's a few properties of perfect squares that you'll probably learn if you do similar questions like this, but it all comes down to experimenting and seeing if you can try and find a set that works. And if you do, good. If you can't find it and you've tried long enough, maybe it might be better to think about the opposite. Can you show that it will never work? So we're choosing 4 because it has a kind of square already in it. So when we factor out the 4 to the k, it has a square already in it, so it can't match any odd factors from the other side. So we're trying to force in an odd factor. Perfect squares are ones where every prime power is like an even prime power. You've got 2 squared, you've got 4 to the 20, right? It's an even power. If we have an odd factor in there, then we're good to go. So as long as everything that we're able to factor out of these doesn't have an odd factor, then we'll be left with odd factors in the other half.
Ethan, how would you summarize maybe the reason that 3 times 4 to the I is a good choice for this set?
Yeah, it's kind of hard. So we're kind of looking for every term here itself is not a perfect square because we always have an odd factor. And we try and find a way that when we add them together, we can still always force in an odd factor somehow. So if you experiment around a little bit, powers work really well because every time you pull out a power, it's an even kind of thing, right? Every time you pull out a 4, you've got an even power there. So whatever's left over, as long as you can show that like once you reduce it down, you get an odd power in whatever's left, you're kind of good to go from there.
Great. I think we'll move on just because we need to finish in time.
Mm-hmm.
So we'll talk about divisibility. You probably already have an intuitive understanding of a lot of these topics that we're going to talk about. But I think it's good to see the formal definition sometimes. So divisibility just means that something is 0 mod something else. So you can see that 2 divides 4, which divides 12, because each successive one is a multiple of the previous one. And the same way 2 divides 6, which divides 12. And you can also see that 2 divides 12. We'll talk more about some of those properties.
Aiden, there's a question in the chat. How long would be given for the previous question, do you think?
I think the Simon Marai is 2 or 3 hours, and it's 5 questions and 2 sessions of that. So it depends how much time you want to spend on it in an actual competition setting, to be honest. But I would say that's not a particularly hard problem as competition problems go, which maybe is a bit scary. But I think if you practice, you'll see these kind of patterns, and something like that should not take too long to come up with, in my opinion, if you come up with it at all. And if you don't come up with it, then it will take much longer. So I don't think that the average amount of time is very representative. It's more like, yeah, maybe takes 5 minutes or you don't get it. And there's a few questions like that in competitive mathematics where you need to have a particular perspective on the problem, and then the solution becomes easy. So you'll notice that when we say 2 divides 4 divides 12 and 2 divides 6 divides 12, they're in ascending order. And divisibility is actually a bit like an ordering of positive integers, but it's more nuanced than that. So first of all, like we saw with modular equivalence, it's transitive, which just means if you have 2 divides 4, 4 divides 8, then 2 divides 8. And that's pretty easy to prove if you just break this k number down into 8 is 2 times 4. And 4 is 2 times 2. So 2 divides 8. We also say that it's reflexive, just like modular equivalence. So everything divides itself. That one's pretty simple. And it's also anti-symmetric, which is something that modular equivalence and equality doesn't satisfy. We say that either A divides B or B divides A, but it's never both unless they're equal. Just like how you can't have a number that's bigger than another number, but also smaller than it, unless they're the same number. Bigger than or equal to, smaller than or equal to, sorry. But it's different to greater than, less than, because not all of those pairs have either A divides B or B divides A. If you look at the second point here, 2 divides 4 divides 12 and 2 divides 6 divides 12, but there's no nice divisibility relationship between the one in between, 4 and 6. So it's not quite the same as greater than or equal to and less than or equal to. Just like modular equivalence is not quite the same as equality. It's kind of a looser version of it. So we'll jump into a Kahoot regarding divisibility before we go into examples. I hope you all still have your Kahoot windows open. I should probably have told everyone to do that. Does anybody need more time to get ready? Cool. All right, let's go on. I think this is a mod question. I hope you can see why that's an odd question. Usually when people introduce modular arithmetic, they talk about clocks, because that's the most intuitive place people would have experienced that kind of addition before. Cool. All right. So
I think option A divides BC is also correct.
yeah, both of them correct. You guys understand it. Yeah, so properties like that are the reason it's important to know the formal definition of divisibility. C equals Ka, B equals Ka. You can factor out a K from the addition, and you can see that BC is can be written as a multiple of A for that same reason. So any number divides 0. I'm not sure about this question. You guys will get that right. I think we'll quality check these questions next week.
Oh wait, I think it means zero can't divide any number.
X divides 0. All right, that one's pretty simple. Cool.
All right, so I'm taking this question. All right, so divisibility example question is show that for any non-negative integer n, we have this sum of powers 1 to the n plus 2 to the n plus 3 to the n plus 4 to the n. And we have to prove that this expression is divisible by 5 if and only if n is not divisible by 4. So what we can see is it says if and only if. So another way of expressing that is this expression 1 to the n plus 2 to the n and so on is divisible by 5 exactly when n is not divisible by 4. So what it means is if the first half of the statement is true, so the number is divisible by 5, then it must follow that n is not divisible by 4. But also the converse is true, meaning that if n is not divisible by 4, then the expression is divisible by 5. So all you can see is this question may look quite daunting at first because we have these powers. We're taking numbers to the power of n, and they're different numbers, and we take into power of n and we're adding them together. And somehow we have to find out when this number is divisible by 5. So for questions like these, what we can do is examine small cases of n or small values of n. All right, so there's a solution there, but we can also do some analysis to figure out the motivation for this solution. So let's see what happens to each of these individual terms. So 1 to the n and 2 to the n. So what happens to these individual terms when you take them to the power of n? So let's start with number 1. So 1 to the power of n is always going to equal 1 when n is a non-negative integer. So this will always equal 1. So what happens to 2 to the n? We can use modular arithmetic to find the remainder when 2 to the n is divided by 5. So when n is equal to 1, actually we'll start with n equals 0 because the question says non-negative integer n. So when n is equal to 0, we'll have 2 to the n is equal to 1. And now we'll do some small values of n. So when n is equal to 1, 2 to the n, that's equal to 2. And when n is equal to 2, you'll get 4, as 2 to the 2 is 4. When n is equal to 3, 2 to the n will equal 8. But since we're working in modulo 5, we can subtract 5 from 8, and it turns out that 8 is congruent to 3 in mod 5. And if we go n equals 4, we will get 2 to the 4 is 16. And if we subtract 3 5s, you'll get 1. So it'll be congruent to 1 modulo 5. Now what we can do is, when we take successive powers of 2, so the next power of 2 will be n equals 5. What we see is 2 to the 5 is the same as doing 16 times 2. So we can multiply the 16 by a 2. By using the multiplication rule in modular arithmetic, instead of multiplying the 16 by 2, you can replace the 16 by 1 and multiply the 1 by 2. So when you multiply the 1 by 2, you'll go back to this 2 over here. So that means that 2 to the 5 is the same as 2 in modulo 5. If you multiply by 2 again, so 2 to the 6, it's the same as multiplying this 2 by a 2. So it'll go back to 4. And in fact, you'll get a cycle where when you take successive powers of 2, the values, when you take the modulus modulo 5, you'll actually loop through 1, 2, 4, 8, and back to 1 again, and so on. And in this case, the loop has a period of 4. So every 4 terms, the pattern repeats. So that's one observation we can see just by doing small cases for the values of n. So it turns out that you can also do small cases for 3 to the n and 4 to the n. And it turns out that the values of 3 to the n and 4 to the n modulo 5, they will also be periodic. So it'll be in a cycle and repeat. And for all of these cases, it turns out that if you take 1 to the 4, you'll get 1 modulo 5. And if you take 2 to the 4, you'll again get 1 modulo 5. If you do 3 to the 4, you again get 1 modulo 5. So you can confirm that by calculating 81, and 81 is again 1 more than a multiple of 5. And if you do 4 to the power of 4, you'll get 256, which is 1 modulo 5. All right. So if you can find a power of a number that gives you 1 modulo something, it's very useful, because then you can conclude that the powers, if we take successive powers of, if it takes the power of n for some number, you can see that there'll be a cycle that keeps on repeating. So for example, if you do 4 to the power of 5, it's the same as doing 4 to the 4 and multiplying it by 4. And again, you can replace the 4 to the 4 by a 1. So you can replace this 4 to the 4 by a 1, and doing 1 times 4 will give you 4. So this goes back to 4 to the 1. So again, you can see there's a cycle that repeats. So I think that's enough with the small cases. Now we can try to go about finding a full proof of this statement. Yeah, I'll just erase the annotations. So this is some preliminary working you can do before you write up the full solution. All right, so yeah, we can go to the next slide. All right. So since from the small cases, we can see that values of each power is periodic with a period of 4 when you take a modulo of 5. It turns out we can divide all the values of n into 4 cases, and the 4 cases will be what's the remainder when n is divided by 4. So we can split an infinite number of cases, infinite number of numbers n, and group them into 4 cases to make the problem easier. So it's a lot easier than trying to do the same problem for infinite numbers of n. So that's why splitting this problem into 4 cases is really useful. So the first case is when n is a multiple of 4. So if n is a multiple of 4, you can write n as 4 times k for some non-negative integer k. So now we can replace this expression over here with all the exponents being 4 times k. So now what you can do is you have this 2 to the 4k here. You can write this as 2 to the 4 and then to the power of k. And we can again use our modular arithmetic rules for exponentiation. We can replace this 2 to the 4 with a 1, which we have derived earlier. This is the same as a 1 in modulo 5. So we can actually replace this with a 1. And in fact, we can do the same things for all these powers over here. So if you do the same process for all these 4 powers, it turns out that adding these 4 massive numbers together is just the same as adding 1 plus 1 plus 1 plus 1 in modulo 5. And that gives you 4 modulo 5. So using modular arithmetic rules, we have reduced this massive number into just a few 1s in modulo 5. So that's why modular arithmetic is really powerful. So when you have massive numbers and massive powers, you can very easily simplify these expressions and make the numbers a lot smaller and easier to work with. So in this case, we see that 4 modulo 5 is not divisible by 5, because we want a 0 modulo 5 for it to be divisible by 5. So this proves that if n is divisible by 4, then the expression is not divisible by 5. And in fact, that is the contrapositive of one of the directions we want to prove. So this proves that if the expression is divisible by 5, then n is not divisible by 4. So what we proved here is the contrapositive of the forwards direction. All right, so we can move on to the next slide. So now the second case is when n is 1 more than a multiple of 4. So let's we'll analyze this case. So let's take 2 to the 4k plus 1 as an example. We can write 2 to the 4k plus 1 so using exponent laws, we can write as 2 to the 4 and then to the power of k, and then multiply that by 2 again. So that's just using exponent laws. And now remember from earlier that 2 to the 4k is this the same as 1 in modulo 5. So we can replace this with a 1. And now we'll just be left with a 2 modulo 5. Yeah, so this is why 2 to the 4k plus 1, you can just replace it with a 2 in modulo 5. And we can do a similar process with the other numbers. So if we just split up these exponents, you can get that 1 to the 4k plus 1 is 1 modulo 5, and so on for 3 and 4. So it turns out that this massive number over here is congruent to 1 plus 2 plus 3 plus 4, which is 10. And 10 is divisible by 5, so that's the same as 0 modulo 5. So in this case over here, the number is in fact divisible by 5. So that's the second case. So yeah, we can go to the next dot point, which is, this is the third case, which is n congruent to 2 modulo 4. Again, we can do a similar process. So if I use this example over here, we can write it as 3 to the 4 and to the power of k. And now we're timesing it by 3 squared. So again, 3 to the 4 is the same, 3 to the 4k is the same as 1. So this is going to be the same as 1 times 9. And that's just 9 modulo 5. So we can do a similar process with the other numbers. So 4 to the 4k plus 2 will just give you 4 squared, which is 16, and so on for these other numbers. And in the end, we'll get 1 plus 4 plus 9 plus 16, and that's equal to 30, which is 0 modulo 5. So again, in this case, n is 2 mod 4. The expression will again be divisible by 5. So now we can move on to the final case, which is the next stop point, which is n is congruent to 3 modulo 4. So again, we can do a similar process. So if I just use an example of 4 to the 4k times 4 cubed is just the same as 1 times 4 cubed, which is 64. So 4 to the 4k plus 3 is just the same as 64 in modulo 5. And we can do the same thing with these other numbers. So you just get 3 cubed, 2 cubed, and 1 cubed. And if you add these cube numbers together, you get 100. And 100 is 0 modulo 5. So in n congruent to 3 modulo 4 case, the expression will again be divisible by 5. So that's all the cases, that's all 4 cases done. So what we see is when n is not a multiple of 4, the expression is divisible by 5. So in these 3 cases, the expression is divisible by 5. But when n is a multiple of 4, we see that the expression is not divisible by 5. So that's enough to prove that this expression is divisible by 5 if and only if n is not divisible by 4. So this first case over here proves one direction of the proof. So the first case proves that if the expression is divisible by 5, then n can't be a multiple of 4. And the last 3 cases over here prove the reverse direction of the proof, which is if n is not divisible by 4, then the expression is divisible by 5. So yeah, that concludes the proof and also some of the motivation for how you can come up with this proof.
Great. Yusiri, do you think you could relate this to Fermat's little theorem?
Oh yes. There is a faster way of dealing with these cases, or at least looking at the values of 1 to the 4 and 2 to the 4 and so on. So what we see is that we're working in modulo 5, which is a prime number. And if we recall Fermat's little theorem, it states that the P is congruent to A modulo P. All right. So we can replace P with a 5. So the prime number we're working with is 5. So one problem is we have an exponent of 4, but this theorem requires an exponent of 5. So we'll have to get around that somehow. It turns out that in modular arithmetic, you can divide by both sides. So you can divide both sides by A. And this only works when the number you're dividing by is co-prime with the modulus. So this works when GCD, the greatest common divisor of A and P, is equal to 1. So the greatest common divisor of A and P is 1. So this only happens when A is not a multiple of P. So if A is not a multiple of P, it turns out that you can divide both sides by A in Fermat's little theorem. And it turns out you'll get A to the P minus 1 is the left-hand side, is congruent to 1. That's A over A in mod P. So this is true whenever A is not a multiple of P. So now if we go back to the problem, we see it's possible to deduce that all these numbers to the power 4 is 1 mod 5 without doing any computations, because the numbers 1, 2, 3, and 4, these are all not multiples of 5. And we see that 4 is equal to p minus 1. So what we can do is we can sub in a over here. We can sub in a equals 1, 2, 3, and 4, and we can substitute 4 p minus 1 equals 4 into this modified version of Fermat's little theorem. So we can immediately deduce that 1 to the 4 is congruent to 1, 2 to the 4 is congruent to 1, and so on. That can save a bit of time. Instead of having to calculate all the powers, so you can, instead of doing a lot of calculations, you can immediately deduce that each of these powers is congruent to 1 modulo 5. So that's how you can relate this problem to Fermat's little theorem, just to speed up the solution.
Does anybody have questions about that one? Cool. So we'll move on to talking about primality and coprimality, which are just the properties of being prime and the property of being coprime. So you probably know what these are already, but again, it's good to see the formal definitions of things because that lets you expand the setup of the problem and break it down into the definition, which often lets you see patterns that you can exploit to a solution. So we'll go over 2 ways to define a prime. One very abstract, generic way to define a prime is whenever you have a product of 2 numbers that's divisible by p. P is a prime if and only if it has to divide each of the numbers in the product. A different way of saying the same thing is if it's equal to some product, then the absolute value of one of the elements in that product has to be 1. And this is just a fun little fact about primes. If you pick any integer n and you double it, there's always going to be a prime between those 2. Coprimality is a more general notion that involves 2 integers rather than just 1 integer. So we say that 2 integers are relatively prime if whenever a number divides both of them, the number has to be 1 or -1. And that's related to up here, the fact that we're saying 0, 1, and -1 cannot be prime. 1 and -1 are called units. They're kind of a special case here. A different way of saying that 2 numbers are relatively prime is that their greatest common divisor is 1. Sometimes you'll see it written just with the brackets, but that's a little bit ambiguous. So unless that's in the question, probably don't use that notation, except maybe in very rough working out, just because people might not understand what you're saying. Let's go to the Kahoot first of all, and then we'll jump into more examples. Does anybody have questions about primality? All right, start in 5 seconds. Cool. For the green option, number 4, the GCD would just be P, because you've multiplied each of them by P. They now share a factor of P, and they didn't share any factors before. So the greatest common denominator would be P instead.
Oh, yeah, I think this question may be flawed because if you make A equals P and B equals 1, then then AB will equal P. So P is a factor of AB.
Yeah. So there's some restriction on those AB. Cool. Great. Yeah, so if they're not coprime, first of all, A and B, then the smallest common multiple is not going to be their product AB. It's going to be their product divided by the greatest common divisor. You can see this by looking at prime factorizations of the numbers. The smallest common multiple is going to be their product divided by all the factors where they overlap, because you want to get it as small as possible. I hope that makes sense. Please ask questions about it if it doesn't. So this one's a little bit tricky. You need to look at divisors of A, B, and A minus B. If something divides A and B, then it's also going to divide A minus B, because A minus B will be 0 mod that something, is one way to look at it. So it's certainly a divisor, and it will also be the greatest common divisor, because of, you can't introduce a bigger divisor by adding and subtracting multiples of that where the multiplicative factors are coprime. I'm not sure if that's a very convincing explanation, but the best way to see all of these properties is to apply the definitions and come up with a proof yourself on paper. It's not, a lot of these aren't really something you can understand just by hearing them or reading about them. You have to go and prove the properties yourself. And we'll put these questions up on the Discord so you can go over them again. Cool. So this question is more one about intuition than derivation, to be honest. But it looks like there are more co-prime pairs than you guys think there are, which is helpful to know when you're trying to guess at possible solution pathways for coprimality questions. It's nice to have some kind of intuition about the structure of the objects you're working with. So this isn't something you can derive very easily in 20 seconds, but it's nice to have an understanding of the general proportions there.
Yeah, for this question, is a fun fact is, so you have number 100,000, or if you take the probability that they're co-prime and take the limit to infinity, it actually turns out your final answer actually has pi in it, the probability. So you could try to derive the probability and see how pi is involved in the answer.
That's a little bit tricky. But yeah, I think it's 6 over pi squared.
Yeah,
That probability.
Yeah, in fact, use the sum of the reciprocal square numbers.
Yeah, so the reciprocals of all the squares add to pi squared on 6, which is 1 over that probability. So that's a good thing to know if you ever have this question again. Good job, Dallas. All right, great job, Fermat. Wonderful. Okay. I hope that was fun, even if not all the questions had correct answers. Let's get back to the workshop. Does anybody have any questions about primality or coprimality before we jump into examples? Cool. Ethan, were you taking this one?
I think I'm taking this one.
Cool.
Yeah. All right. Yeah. All right. So let's have a look at this question. If n is a positive integer such that 2 to the power of n minus 1 is a prime number, we have to prove this implies that n is a prime number. So if you're thinking in terms of methods of proof, you can kind of see a direct proof isn't too easy for this question, because if you made 2 to the n minus 1 a prime number, it's not that easy to see how to proceed and directly see why n has to be a prime number. So all we can do is try proving the contrapositive, which is pretty interesting. So the contrapositive means if the second half of the statement is not true, then prove that the first half of the statement is not true. So if I write the contrapositive down, it will be if I might use text. So if n is not prime, implies that 2 to the n minus 1 is not prime. Oh wait. Yes. Yes. So text is there. So the contrapositive is if n is not a prime number, then we have to somehow prove that 2 to the power of n is not a prime number. And the reason the contrapositive is useful in this question is because if n is not a prime number, we can immediately deduce that we can write n as the product of 2 integers that are at least 2. So I think, yeah, you can go to next stop points because I'm pretty sure it's, yeah, the stuff's already here. Yeah. Yeah, so in the contrapositive, so yeah, we can let n equals xy, where x and y are at least 2. Yeah, so this follows from n being composite number. So now we've got 2 to the n minus 1 is equal to 2 to the xy minus 1. So now we could analyze some small cases to see why 2 to the n minus 1 is not a prime number. So let's make n is equal to 6. So when n is equal to 6, we can make x equals 2 and y equals 3. If we do 2 to the power of n minus 1, that's 2 to the power of 6 minus 1, which is equal to 63. And 63 is equal to 7. 63 is not a prime number, so that's good because it shows that what we want to prove is correct for one specific value of n. So you can write 63 as 7 times 9. And now if we examine number 7, it turns out that 7 is equal to 2 cubed minus 1. So 7 is 1 less than a power of 2, which is pretty interesting. So you can also do a slightly higher case, such as the power of 10 minus 1, which is equal to 1024 minus 1, which is 1023. And again, we can write 10 as 5 times 2. Now, we can try to see whether or not 1023 is prime or not. And it turns out it is not prime because it is divisible by 31. So if you manually check check for prime factors of 1023, you can find that 31 is a prime factor of 1023. And it turns out that 31 is equal to 1 less than a power of 2. So it's equal to 2 to the 5 minus 1. So we've got some interesting results over here. So it turns out that we've got so what we see is 7 was 2 cubed minus 1, and we made y equal to 3. And also 31 is 2 to the 5 minus 1. And remember that 10 was equal to 5 times 2. So you see there's a 5 in common there and a 3 in common in the previous example. So then using that, we could conjecture that 2 to the x minus 1 is a factor of 2 to the x y minus 1. So this is supported by those examples I used earlier of using 2 to the 10 minus 1 and 2 to the 6 minus 1. So the question is our conjecture 2 to the x minus 1 divides 2 to the xy minus 1, is our conjecture correct? And in fact, we can prove that this conjecture is indeed correct. So we can go to the next dot point. You might remember from high school that you can factorize a to the n minus 1 as a minus 1 times a to the n minus 1 plus a to the n minus 2 and plus, so dot 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 and plus 1. So we can use this factorization over here. So we're going to make a equal to 2 to the x, and we're going to make m, going to replace this n over here with a y. So if we do that, this a minus 1 over here will just be 2 to the y minus 1. And then we can also substitute, oh wait, actually they did it the other way around. So in fact, the solution over here had a y here and an x here. So we've got,
I might jump in. Sorry, Yasiru. I might just point out, if this identity is confusing to you, dividing by a minus 1 on both sides, you'll see that it's just a geometric series. So that's perhaps a good way to remember that kind of identity. It's just a geometric series formula. Thanks, Yasiru.
right. Yeah, so I can substitute your values into this a to the n minus 1. So you get 2 to the y minus 1 for your a minus 1. And you've got the sum of all these terms over here. So that's the sum of all these powers of a. So I can see is 2 to the y minus 1 will be a factor of 2 to the xy minus 1, because 2 to the y minus 1 is an integer, and this massive sum over here is also an integer. So 2 to the y minus 1 will be a factor of 2 to the xy minus 1. All right, so yeah, we can go to the next dot point. So we've found a factor 2 to the y minus 1 of 2 to the n minus 1. And remember, so x and y are at least 2. So it means y is at least 2, so 2 to the y minus 1 is greater than 1. And also, since x is at least 2, then y is less than n. So since y is less than n, 2 to the y minus 1 is less than 2 to the n minus 1. So we've found a factor of 2 to the n minus 1 that is not equal to 1 and not equal to itself. So it's between those two numbers. And that is enough to show that 2 to the n minus 1 is a composite number, so it cannot be a prime number. So we have got our contradiction over here. In fact, we can, instead of saying contradiction, we can also say that we've proved the contrapositive. So you can say n not being a prime number implies that 2 to the n minus 1 is not a prime number. So you can phrase it in either way. If you're doing proof by contradiction, you can phrase your proof. You can phrase your proof as assume 2 to the n minus 1 is prime and n is not prime, and then you can say you can reach your contradiction by deducing that 2 to the n minus 1 is not prime. And you can also phrase it using proof by contrapositive, which is, so assume that the second half of the statement is not true, so then prove that the first half of the statement is not true. So both ways are perfectly fine, and in fact they are, proof by contrapositive and contradiction are almost identical in this case. So we can do a quick recap of this proof. So we assume that n is a composite number. We write n as the product of two numbers at least 2. And using our index laws and factorization, we found a factor of 2 to the n minus 1, which is not equal to 1 and not equal to itself. So that's enough to show it's a composite number. So that's our, so then then our statement will be proved by either contrapositive or contradiction. So yes, that concludes this problem. Yeah, so n must be a prime number in order for 2 to the n minus 1 to be a prime. Some more remarks about this question. So when n is a prime number, this number 2 to the n minus 1, this is called a Mersenne prime. Mersenne prime. So any prime number that's of the form 2 to the n minus 1 where n is a prime number. So an exercise for the reader could be, so first exercise could be when n is a prime, is 2 to the n minus 1 always prime? So that's one question you can keep in mind. And another remark is the largest prime numbers that have been discovered so far have been Mersenne primes. So if you make, so I'm pretty sure the largest largest prime number currently known is a Mersenne prime where n is around 50 million around. So you can use Mersenne primes to figure out, try to find the largest primes that are out there that are currently known. Yes, that concludes this example.
Anyone here who's also interested in competitive programming might want to note that the reason that the biggest primes found so far have been Mersenne is that there's a very efficient algorithm for testing the primality of Mersenne numbers, 2 to the n minus 1, for general n. And that scales very nicely in big O time, for those of you to which that means something.
Alrighty, so let's do some annotation. So this question here is, I can't clear off the red lines. Someone will have to, I might be able to. No, I can't clear off the red lines. Someone else will have to do that. But so this is kind of similar to the previous one that I did, which was whether or not there are a certain amount of distinct pairs, right? This time we're given that there are. So we're proving that this is a truthful fact. So to do that, we need to be able to construct infinitely many distinct primes, or we could also suppose maybe another way, which I tried fiddling around with but couldn't get anywhere, unfortunately, is to suppose that there are only finitely many distinct pairs, because there's definitely at least one. Suppose that there's finitely many distinct pairs, and then see if you can construct a larger pair. That's another way that might show up in different questions. For this one, doesn't really work out. At least I wasn't able to make it work out. So it's a little bit scary looking at this question because we have some kind of ugly exponents here, right? And we're looking for divisibility by a plus b. So when you're looking for divisibility by a number, you usually want that number to be multiplicative. Dealing with divisibility by adding two numbers together is kind of ugly. So we tend to try and make the divisor something relatively simple. So the first point here is to note that we want a plus b to be simple. And we also want like a and b on their own to kind of be simple. So next point, we have if a and b are both, is it just not updating for me, or like next slide? There we are. Okay, so we want a factor of a plus b, and we want to keep it simple. So we can try a and b being 2k plus 1 and 2k minus 1, for example. So this choice here is first by noting, first of all, if we have two even numbers, so 2 times k and 2k prime, then yeah, the sum would be simple, right? But between these two here, you have a common factor of 2. So we require relatively prime integers, which ruins that case. So instead, we might consider, what if we had one that's odd and one that's even? So we could have 2k and maybe 2k plus 1. So this is relying on the fact that consecutive integers are coprime. So these are coprime, that's fine. But you're going to end up with 4k plus 1, which is kind of ugly. Again, you've got this little addition here that you don't really want. So maybe try something else. Now, of course, all of these are things you can try and maybe try and go further with. But I tend to begin with the more simple cases. So the simple case here being 2k minus 1 and 2k plus 1. So these two are coprime. You can prove that pretty easily using the Euclidean algorithm to find the GCD as 1. But they're coprime, they're both odd, but when you add them together, you're just going to get 4k, right? So the plus 1 and the minus 1 cancel that, and you've got something that's kind of multiplicative. So it's a good start, right? Now, so starting off with these numbers here, we can try and figure, so, okay, we've got A and B, right? So what we need to show, the next point, is that 2k plus 1 to the power of 2k minus 1 plus 2k minus 1 to the power of 2k plus 1 has a factor of 4k. So the factor that we're dealing with is relatively simple. And the crux of this argument is like one line that immediately gives you the answer, right? And it's noticing that if we take 2k plus or minus 1 and we take it to an even power, or just 2 in general, then we end up with, here we are. So if we take 2k plus 1 and we square it, we're going to end up with 4k squared plus 4k plus 1, right? And this is 4, that's a really bad 4, times something plus 1, which means modulo 4k, sorry, 4k times something. Modulo 4k, we have 1. So you may have seen earlier that when we had this kind of, it wraps back around to 1, we can cancel those out when it comes to modular arithmetic. And that's exactly what happens here. So when we take the second power, next slide, when we take the second power of either 2k plus 1 or 2k minus 1, we end up being able to split it into our 2k plus 1, gets split up into the square part of it. So we have 2k minus 2, and then we have one extra factor of 2k plus 1. And this is kind of like a more primitive way of saying that it's 1, kind of. So we have this here is 1 mod 4k. So when you multiply by anything else, you're just going to end up with 2k plus 1, and then you're going to have something mod 4k, right? And you can get something similar with this one. You're going to end up with 4kn plus 2k minus 1, right? And because we're dealing with everything modulo 4k, this 4k here and this 4k here kind of disappear. And we're left with 2k plus 1, 2k minus 1, which is exactly a plus b that we came up with. So certainly a plus b is, which is 4k, right? A plus b here is certainly a divisor. So if we continue along, we end up expanding out everything, and you end up with something kind of ugly. But basically all I'm saying here is you've got a factor of 4k, and then what's left over is 2k plus 1, 2k minus 1, which ends up having a factor of 4k, right? So 4k here is definitely a divisor. And finally, since this works for literally every number of k, so if k is greater than 1, then these two numbers here are definitely greater than 1. So remember the condition up here, a greater than 1, b greater than 1. If k is greater than 1, then we've found a case where this is divisible by this, and we're good to go. The only thing to check then is if they're relatively prime. Now, when I came up with this, you come up with, yeah, they're relatively prime, right? So we can continue further. But maybe you get to this point, and you can use Euclidean algorithm. So 2k plus 1 is 2k minus 1 plus 2, and then 2k minus 1 is 2k minus 1 plus 1, so the GCD is 1. If you're not familiar with the Euclidean algorithm, it can be convenient for proving facts like this. Look it up, you've probably used it. Maybe you haven't probably used it. If you've done Math 1081, so Discrete Maths, you would have been exposed to it mostly because Discrete Maths at UNSW has a focus on number theory for one of the topics, which can be very useful for answering questions like this. So all of the facts that we've kind of gone through here are also things you would have learned in Math 101. But basically, we add all of this stuff together and we end up with, since GCD is equal to 1, and we can take any k greater than 1, there are infinitely many distinct pairs satisfying the conditions required. So yeah, we've found basically a family of solutions, which is all we need. There are many other solutions, by the way. You can take any, I've seen another one where they take, instead of 2 times k plus 1, 2k minus 1, they just take powers of 2, which is kind of a subset of this solution. There's other ones where you take one of them odd, one of them even, and then you can do some funky stuff with that. You can take the a plus b, another approach, a to the b plus b to the a, and then add some extra assumptions on relationships between a and b that help you simplify this relationship. So maybe you could make it so that a plus, so maybe if b is odd, right? You can say, yeah, I won't go into this. Basically, there are alternate solutions to this, but the approach here is to try and come up with simple numbers and see if they work. Obviously, there's the kind of assumption that you know that it's true to try simple examples to try and find some kind of family of relationships. If you don't know if it's true or not, sometimes it will end up being really complicated and you kind of, so you'll start off with some simple solutions. They seem to work, but maybe you find a counterexample later on and it's actually false because although you've tried some simple solutions, maybe none of them worked. There's a more complex solution. There's a bunch of things. It's more, since we know that there definitely are infinitely many distinct pairs, we can start off with simple pairs and see if they work, right? Because there's definitely going to be a solution. It comes down to if you can find a solution that's easy to work with and easy to prove is correct. Yeah. I rambled a bit there, but that's basically it. Any questions or anything about that? Does any prime AB work? So if you took just any relatively prime numbers, are you talking? So if both A and B are prime, I don't believe it. Yeah, I don't believe it works in general. Because if you take, you're still going to get a factor of 2. So the factor of 2 works out fine. Maybe we could do Fermat's little theorem. Should give you a factor of A plus B. Should it? I'm not 100% sure about that one. Yeah.
Oh yeah, the issue is
I think if you take,
yeah, you're working in modulo A plus B, but problem is Fermat's little theorem only works for modulo prime numbers. So A plus B is not necessarily going to be a prime number if A and B are prime. So that's the issue with that approach.
Yeah, because you'll have definitely a factor of 2 in this. It'll be an even number, which definitely can't be prime. Yeah, so you're not able to apply Fermat's little theorem here. I don't think it works in general for any prime numbers. I could probably come up with an example.
I don't think 2 and 3 works.
2 and 3. So we have what, 8 here plus 9, which is 17, which is definitely not divisible by 5, right? Yeah, that works. So if A and B are prime in general, doesn't really work. Any other questions or notes or anything?
Thanks, Ethan. I think that one was a bit algebra heavy, maybe. What would you say is the main thing to take out of this solution?
Yeah, I guess, I mean, it showcases why modular arithmetic is so nice because all of this avoids using mod, right? But you can very easily say something like 2k plus 1 squared is equivalent to 1 mod 4k. And then from there, you can simplify this in like one line instead of going through this. So it's nice for that. I think the main takeaway though is just for approaching questions like this, if you're asked to prove that there are infinitely, so this question shows up quite a bit, prove that there are infinitely many distinct pairs or distinct numbers such that some conditions hold, right? You know that they must exist, otherwise, well, hopefully, otherwise they would state in the question that disprove, right? So you know a family exists. The question is how you can come up with them. And it comes down to, I guess, drawing on your knowledge of, in this case, number theory. So I know that when we're dealing with divisibility, we like things to be simple. So we try and simplify a plus b. And I know a couple of coprime, relatively prime integers, right? I know like k and k plus 1. Consecutive integers are coprime. I know that if you take a number and you go one left and one right of it, so 2k minus 1, 2k plus 1, they're relatively prime. You can start looking at prime factors, but when it comes to powers like this, it might be a little bit difficult to deal with them because we're now adding across it. So prime factor analysis might be very difficult for questions like this. And noticing that because we're trying to find a factor of 4k, that 2k plus 1 squared gives you 1. Once you find that, everything kind of falls into place. So it's looking at kind of the structure of the question and applying some of the number theoretic things you'll pick up from other questions, just random facts that you might be able to bring together, and also looking for simple solutions. If you're looking for solutions, look for the simplest solution you can, because usually they're the easiest to prove. There may be more complicated solutions. They're usually a pain in the ass to prove.
Thanks, Ethan. It's 8:30 now, so I think we'll wrap it up there. If anyone has any questions, feel free to ask them. I'll stick around and try to answer them. Otherwise, feel free to jump out if you need to get somewhere. Probably end the call at 8:40 maybe. Thank you for coming. 2 weeks as usual.